Hello, my name is Jacob Schrader. This presentation is for ME 575, Materials for Additive Manufacturing, focusing on reactive polymers, and my specific material for this paper was bismalamides. From this point on, I'm going to call them BMIs. So the title of this paper was 3D Printing of BMIs from New Ink Formulation to Printed Thermosetting Polymer Objects. There were several authors of this paper, so I'm not going to read them all, but they are shown there on the second line. This paper was published in the Advanced Material Technologies Journal in 2019. So the specific scope of this study is to understand the development of the first BMI-based ink for polyjet printing. And then, so to do this, the researchers addressed a couple different questions. First is to find the correct dilution material used in combination with the BMI to allow it printing in the polyjet. Second, to understand the chemical conversion of BMI during a post-curing process. And then lastly, to understand some material properties of the BMI after it has been printed. So the materials used here are obviously BMIs, so the specific material these researchers use is BMI-689. So that material cannot be directly printed with the polyjet, so they have to dissolve that in some solvents, and to do that they used BMI-689 in an 80% by weight hexyl acetate solution and 3% photoinitiators to create a material called DIPI ink. So first the researchers looked at some different methods of the BMI curing, and then they looked at a couple different material properties and they compared those in the printed and casted BMI samples. So to do this, understand material properties, they look at first the chemical conversion of BMI during the curing process using an FTIR, and then lastly they look at the material properties first using a 3-point bending dynamic mechanical analysis to understand Young's modulus and storage modulus, and then finally some temperature testing to understand the thermal decomposition stability of the printed DIPI material. So the first key result of this study is to understand the chemical conversion of BMI during the curing process. So they looked at the material in four different forms. So first it was a liquid DIPI ink. Second was a printed DIPI with no post-curing. Third was this printed DIPI ink with the post-curing process. And then lastly was just a casted BMI 689 ink. So the key point the researchers are looking for here is to understand if the solvents that were used to create the DIPI ink solution fully evaporate during the printing process. And you can kind of see that on the right, that the first line there in the red ink is the DIPI ink in liquid form, and there's peaks for the hexyl acetate solution, and as you move down to the blue, green, and black line, those peaks are gone, which means that in printed and then printed with post-curing, and obviously in the casted BMI, there is no presence of the hexyl acetate solution, which is critical to achieve good mechanical and thermal properties. So the researchers were able to prove that in printing and also in printing with post-curing that the ink fully evaporates. The second result of the study was to look at the material property analysis of the BMI material. So first, with the graph on the far left there in the middle, the researchers looked at the storage modulus, and they evaluated storage modulus at multiple temperatures and curing time. So it can be seen on this graph that the storage modulus increased with the curing time up to 275 degrees, and then at 300 degrees Celsius and above, the storage modulus started to decrease with curing time. The second material property the researchers analyzed was the Young's modulus and the stress at break. So they evaluated these at multiple temperatures and different manufacturing methods, and were able to confirm that the max Young's modulus was for printed DIPI ink post-cured at a temperature of 275 degrees, which is shown in the top right of that Young's modulus graph there in red, where all their points are shown in blue. Lastly, the researchers looked at the thermal degradation, comparing printed and then printed with post-curing. So obviously you can see here on this right, the blue line is just printed, the red line is printed with post-curing, and it's obvious here that thermal stability dramatically improves with the post-curing process. So some key conclusions from this paper are 3D printing of the DIPI formulation does not compromise any of the pure BMI 689 properties. Secondly, they were able to prove that a BMI-based ink formulation, here they call it DIPI, can be used for polyjet printing, which is the first time that this has been done in the industry. And then lastly, they were able to prove that post-printing treatment is critical for achieving good mechanical and thermal stability of the material. So some personal critiques from me on this paper are: this was a very detailed analysis of important material and thermal properties of BMI, which is critical to understanding if it can be used in the industry. This paper does not spend a lot of time discussing specific industry applications for BMI and why it should be used over other materials, so I'd like to see some more of that. And then lastly, I would like to understand the cost of BMI compared to other materials in the market, and why it hasn't been researched before, and why these researchers are just now starting to look at it in 2019.